I've been hoping for this day or evening for some time, trying to get Charles to commit from his busy schedule to come and talk to our students. And I had known him for a number of years. He was a very successful full professor at UCSD and decided he wanted a different challenge, I expect. And so he went to Amazon in 2014 to lead their machine learning team. I kind of anticipated that he would still be there when I tried to reach out to him, only to find out that he had moved on to Goldman Sachs to lead their machine learning efforts. So I think in some sense, Charles is one of those unicorns that is both able to excel at the highest levels of academia as well as in industry, which I think is very unusual, which makes his talk, I think, one of the more interesting ones in that he doesn't just understand at the very, very highest level the technical details of everything to do with machine learning and data science, but also how to implement it and use it in practice. So I think that's going to lead to some great questions. So I'm really looking forward to this talk. Thank you so much for committing to this, Charles. Looking forward to it. And one thing to mention is that if you have questions, please put them in the Q&A box. So not the chat box as usual in Zoom. This is a Zoom webinar, so you'd have to put them in the Q&A box. And then at the end of Charles's talk, I will moderate and ask some of your questions, or if there's not any questions, I'll add some of my own. So thank you again very much for joining us. Charles, take it away.
Thank you, Vincent, especially for the invitation. I wish that this could be in person. I always enjoyed coming back to San Diego, being on campus. I have quite a few friends in the Rady School, and of course, many friends in computer science in particular, because that's the department I was in for a long time. And yeah, as Vincent said, my talk's not going to be very technical. I'm going to be sort of more talking about the practicalities of making machine learning and related disciplines work in commercial applications. And I'm going to talk some about finance, but most of what I'll say will be applicable in other fields. And I should mention actually that I've moved on from Goldman Sachs. I was at Amazon for 4 years and then Goldman Sachs for 2.5 years. And yeah, I can say honestly that though I really liked all my colleagues at Goldman Sachs, the whole culture of Wall Street, the culture of technology companies is more congenial. So actually what I moved on to is I have a startup. I'm not going to talk about that because we're still developing our product. And then actually recently I got recruited. I'm working part-time for Saks Fifth Avenue. You might have seen that private equity has invested in Saks.com. There's a big opportunity to grow luxury and fashion retail and using machine learning and other technologies. So I'm back in retail, which is a lot of what I worked on at Amazon, but of course, Saks is a very different retailer from Amazon. So if anybody has any questions about anything related to my experience or what I'm going to talk about in the talk, then I'm easy to reach, and anyone from UCSD should feel free to reach out to me. The title is Machine Learning in Finance, Lessons Learned. As I mentioned, this is not going to be just finance, and I think a lot of lessons are applicable in other application areas, even outside business, for applications in engineering or science that are outside computer science. I need to find the right button to move the slide forward. Okay, not sure. So, machine learning as a research area has been around for many decades, as this picture illustrates. And machine learning is a subfield of artificial intelligence, which really began in 1956 with a research conference. And this photo is from 1966, so 10 years after the beginning of machine learning. So this photo is more than 50 years old now, or 1967. And the reason I chose this photo is because it shows somebody called John McCarthy, who was one of the founders of artificial intelligence. And actually, I was fortunate that John was my advisor when I was a visiting student at Stanford. And of course, he was much older than he was in this picture. But I really like this picture because it illustrates that the way that people think about big data really hasn't changed all that much. This picture is obviously totally staged, and the tape drives in the back are supposed to make you think of big data, and you're supposed to be impressed by how big the computer is. And then John in the picture is playing chess, and you're supposed to think that he's playing chess against the machine, and you're supposed to think that chess is the ultimate achievement of human intelligence. And in fact, in 1967, people thought that computers might be programmed to beat the human world champion in chess sometime far in the future. In fact, it was in the 1990s, I think, that Garry Kasparov was defeated by a computer pretty soundly. And then it was much more recently that the game of Go, the human world champion, was defeated by a machine learning algorithm. And so if there's one thing we've learned from that, it's that there's a lot that humans do that requires intelligence that actually is much more difficult for software than playing games like chess or Go. So why is there so much excitement about machine learning nowadays? I was doing research in machine learning in the 1990s at UCSD, and I had colleagues also doing research, but I won't name who it was in the administration, but there was a certain senior administrator who pretty much told us to our faces that he didn't understand why UCSD had machine learning research. And of course, it's pretty different nowadays. But the reason there's a lot of excitement now is because there's been big progress in an area called deep learning. And if you're familiar with even the basics of philosophy of science, then you've heard the idea of scientific revolutions. And I think scientific revolutions happen on every scale. There's sort of a fractal phenomenon. And deep learning has been a mini scientific revolution in computer science. It's especially enabled us to solve problems in vision and in the combination of language and vision that were not possible to solve before. And the illustration here is an example of that. So we can have machine learning systems now where the input is a photograph like this one and a question expressed in natural language. There's nothing special about English, by the way. And then the machine learning system will provide the answer to the question, which describes something in the image. So here the question is, how many leftover donuts is the red bicycle holding? And the answer is 3. The reason it says ground truth here is because this is part of the training data. Machine learning systems always need huge amounts of training data, and then really they adapt the algorithm in an automatic way internally, and then you can apply them to additional examples where you don't know the answer, and then the machine learning system gives you the answer. So deep learning, really has enabled some impressive applications, and then for many business applications like forecasting, it has provided significantly higher accuracy than any previous methods. So this is to say a little bit more about what deep learning is. It's the current generation of neural networks, and they're inspired very loosely by neuroscience. There's pretty much a permanent debate about whether the findings from the biology of animal or human brains are relevant or not to artificial intelligence. It's an undecided question. And I mentioned that artificial intelligence really began in the 1950s, and neural networks were invented in the 1950s. There was a lot of excitement, and then people realized what they really couldn't do. And so there was a loss of interest in the field. Then there was a mini scientific revolution in the 1980s with something called backpropagation. And researchers became very excited about neural networks again. And in fact, a lot of this scientific revolution of neural networks in the 1980s happened at UCSD. And UCSD was possibly the leading university in the world in the late 1980s and early 1990s for research in neural networks, if not in all of machine learning. And then deep learning was invented in the 2010s and is what's driving the field currently. Current deep learning uses the power of current computers. The smartphone that you have in your hand really is as powerful as a supercomputer from even 15 or 20 years ago. And deep learning is very computationally intensive, but you can do it on smartphones, and then you can do it on an even bigger scale with cloud computing. And nowadays, it's not just that we have a lot more data than we've ever had before. We have types of data that previously just weren't being used in business or finance. We have a lot of text data, we have a lot of images, and we have a lot of video. And if you take traditional methods from statistics or traditional methods from econometrics for forecasting. They just aren't designed for these new types of data. And machine learning is really the game in town for these new types of data. The illustration on the right here gives you a rough idea of what a simple neural network looks like. So the input is a photograph, and here it's just black and white, and it's 500 by 500 pixels. So this is actually a lot less information than you would have in a lot of input modalities nowadays. And then the neural network is a series of layers, and each layer is doing simple mathematical operations on the output of the previous layer, but those operations are tunable, and they're tuned by coefficients which are called weights. And then there's an algorithm which adjusts all these weights to produce the desired output. So if you look on the right, this is a neural network which has 5 outputs. So these outputs will be 5 numbers. And you can think of these numbers. So the first one, for example, might count how many animals are in the picture. And then the second one might be Boolean. It might say, is there grass in the picture, or is there not grass in the picture? And by doing mathematical operations on all the pixels in the image, eventually you can come up with a number which is 1 if there's grass in the picture and 0 if there isn't grass in the picture. And that's the basic idea of a neural network. Right. I mentioned that neural networks provide the best methods currently for forecasting. So these illustrations are from a paper that people in my team at Amazon published. And the top image really shows the difficulty of the problem. So the top image is 4 different products chosen pretty arbitrarily. And the black line is the pattern of demand for the pictures. And each of these pictures is over a period of about 2.5 years, starting in 2015 and going into 2017. So if you look at the product whose image is at the top left, you can see there's a big spike in demand actually at the end of 2014, I think just before the start of 2015. Then there's another spike in demand at the end of 2015. And then the vertical blue line is the date which we want to forecast future demand. And so it's pretty obvious if you're a human looking at this that you expect there to be another spike in demand at the end of 2017. And indeed, that's what the model predicts, and that's what the reality is. So the black line, which is to the right of the vertical blue line, that's the actual outcome of demand for the product. And the blue line, which you may not be able to see so well, which is below the black line, that's the forecast. And you can see that the forecast definitely expected a peak, but the actual peak was much higher than the forecast peak. But there's a blue shaded region, and that blue shaded region is the confidence interval for the forecasts. And you can see that the actual outcome was just within the confidence interval. So this forecast was actually a success. And the general policy at Amazon is you issue purchase orders so that Amazon is in stock up to the upper limit of the confidence interval for the forecasts. So this was a success that the company didn't go out of stock on this particular product. Then the other 3 panels are totally different products. So the one at the top right, you see this is a product which has very unpredictable demand. There isn't any obvious seasonal pattern. And so for this product, the forecast also doesn't have an obvious seasonal pattern. And then the confidence intervals get wider and wider as you go further into the future. The panel that's to the bottom left, so this is a product that was brand new in the middle of 2016. And so there was very little data before the vertical blue line on which to base a forecast. So this is an example of a product for which standard econometric methods would not succeed at all in making a forecast. But the key thing that's happening here is that as well as the time series of historical demand, the neural network is using the description of the product, is using the actual language, the words to describe the product. So if something is a bikini, for example, then the neural network has learned the general pattern of demand for bikinis, and it can extrapolate that to this new product, which has the word bikini in its description. And that's, the key benefit, or one of the most important benefits of neural networks for applications, that they can use multimodal data. So here it's using the time series, but it's also using the text description. And there are newer versions of this at Amazon and many other companies, which are also using the photographs and any other really available information about the products. So this is an example of something that we can do with deep learning that just wasn't possible without deep learning. This slide is something actually that I just found out about yesterday. It's something that Qualcomm announced in February 2021. And I heard about it from a former student of mine who was the leader of the team that developed this. So, there's antenna design is rather a black art in electrical engineering. And the antennas in 5G phones are the most complex in the world. And, only a few companies like Qualcomm really know how to design these antennas. And there's no perfect simulations of the physics of antennas. And so designing a good antenna is empirical as well as using Maxwell's equations. And so now in the latest chips that are in the latest 5G phones, there's an artificial intelligence subsystem, which is continuously detecting where the hand of the user is on the phone. And the hand of the user is blocking the radio signal to some extent. And so the antenna is actually tuned to overcome how the radio signal is being blocked by the hand of the user. And of course, that's going to depend a lot on where the radio signal is coming from. So this is something which you can do with machine learning, which there's no other technology that would allow this type of continuous tuning of antennas. All right, so what can we not do with machine learning, artificial intelligence? And the way I put it is that we cannot achieve deep understanding. And I define understanding operationally as the ability to answer questions. The systems we have nowadays, they have shallow understanding. They can answer a limited range of questions where the questions are similar to each other. For example, questions like how many animals are in the picture, or is this a picture of a cat or is this a picture of a dog? And what is still impossible to achieve is understanding which has multiple levels, which uses broad context, which uses broad knowledge. And this can sound rather amorphous, undefined. And that's why I like the definition of understanding as being the ability to answer questions, because that's something that's measurable. And it's interesting, if you actually look back at the etymology of the English word intelligence, it comes from a Latin word, which has the root meaning of choosing between. So I like to believe that actually even etymologically, intelligence is the ability to select the right answer. So here's an example of what I mean by deep understanding. So look at this picture again. If you look carefully, you can see that in the white box in the bottom right, there's what looks like half of a donut. And actually, the first time that I used this picture in a talk, it's when I was asked to give a presentation to the board of directors at Amazon about machine learning. And Jeff Bezos is very knowledgeable about machine learning, but most of the other directors of the company are not. And I was impressed. I had just looked at the picture and thought, okay, the answer is 3. But Jeff Bezos put his hand up and said, no, the answer is not 3. The answer is 3.5. And that's a perfect. If you think about it, the answer is different from different points of view. If the meaning of the question, the purpose of the question is how many people can we feed, then the answer is 3, because nobody wants to eat somebody else's half-eaten donut. And then if you think, what can we literally see in the picture? You can see 3 donuts and then you can see 2 pieces. It's only because we know about gravity that we know that those 2 pieces must be connected, because if they weren't connected, then they would fall down and they wouldn't be visible. So and then knowing that the same question can have more than one answer, and then being able to explain the different answers from different points of view, that's what I would call deep understanding. And here it needs knowledge about gravity, and it needs knowledge about social conventions, and this is what we don't have in current systems. You might ask, is deep understanding really needed? And the answer is yes, if you really want very robust performance. The opposite of robust being brittle, something that breaks easily. So just think of a self-driving car and just look at this picture. So most self-driving cars, they would recognize the pedestrian and they would slow down because they've been programmed to be very risk averse. But a self-driving car wouldn't understand why this pedestrian is in the road. Whereas any human who's looking at this picture can immediately understand why the person is in the road. He's trying to protect the duck and the ducklings. And the man, he's not just standing in the road, he's got his hand lifted up. And this is not just a random arm movement. This is actually a signal, it's a symbol. So this man is using language to communicate something to the car. So if a self-driving car is going to be really human level, then it needs to understand this type of language also. And we definitely don't have this level of capability currently. In fact, there are very basic things that are just too difficult for current technology. This is something that I've been trying from time to time for many years now with Alexa systems from Amazon, and I just tried it again today. So actually, I shouldn't say the name of it because then my mind is going to wake up and it's going to be confused. But if I ask it, where is Mount Everest, then I get a very good answer. Mount Everest is located, so on and so on. But if I follow up immediately with the question, how high is it? And I just tried this again today and I got the answer right now, it's 66 degrees Fahrenheit. So this AI system has completely failed to understand the follow-up question. And moreover, it's failed to understand that it failed to understand. It didn't say something like, I'm sorry, I don't know the answer, or I'm sorry, I did not understand the question. And if you, the other thing that's slightly less visible to users is that AI systems need excessive quantities of training examples. And this is connected with not having broad knowledge and not being able to deploy that knowledge. If you've never been to Boston, you might not know the local meaning of the word wicked, but you wouldn't need many examples to figure out what the word means. Whereas any natural language processing machine learning system is going to need a much larger number of examples. I want to talk about how applications can be successful despite the lack of deep understanding. And this happens to be a company that Goldman Sachs has invested in. And I haven't followed them very recently, but I was really impressed by what they were doing when I was finding out about them. So their goal is to make healthcare visits more convenient for patients and then more efficient for the providers, and so less expensive. And currently, the average primary care visit in the United States is about 25 minutes. And they've succeeded in reducing these visits to 9 minutes with the same level of quality and with the same level of patient satisfaction, with the same level of physician satisfaction. So this is really a huge increase in productivity for medical care. And the way the system works, the patient describes symptoms in free text, so natural language, and then the app uses machine learning to select follow-up questions, and the patient answers the follow-up questions. But the app is just selecting the follow-up questions from a set of standard questions. So it's not actually generating new questions. And the standard questions have been carefully written by humans to be informative. And then the physician reads everything the patient wrote and meets the patient. And as needed, the physician can ask for more information. So in the worst case, when the system asked totally the wrong questions, no harm, no foul. The physician just starts at the beginning. But typically, the information that the patient has provided is very informative and saves a huge amount of time for the physician. And the physician still is 100% in control of making decisions about prescriptions, about advice, about referrals. And this is part of the job that physicians and nurse practitioners find the most interesting often. And so whereas asking the routine questions is less interesting for them. So this is really win-win for patients and for providers and for whoever is paying for the medical care. And only the physician needs deep understanding. The machine learning only needs shallow understanding. So what's different about machine learning applied in finance? And one thing that struck me when I went to Goldman Sachs is there are already so many people who are using quantitative methods, and machine learning is a quantitative method. Whereas if you go to a company, well, Amazon, of course, is very technical, but you go to a company like Saks Fifth Avenue, and most people are not using quantitative methods. And so then you could say machine learning is more novelty. But in finance, machine learning is continuous with the existing methods. And I'd say the basic difference is that machine learning is fundamentally empirical, while the other methods tend to be deductive. And Black-Scholes is an example. So if you start with some axioms about arbitrage free, then with some amazing mathematical derivations, you get the unique rational price for an option. And Black-Scholes, you don't need to go out and look at the real world to see whether Black-Scholes is true or not. It's mathematics. It follows from the assumptions. It follows from the axioms. But then if you go out and you do look in the real world, you find that Black-Scholes prices are not accurate, that they're a good starting point, but they're definitely not perfectly accurate. And this illustration on the right is something called an implied volatility surface. And so the vertical axis is volatility, and Black-Scholes is based on the assumption that volatility is constant. And empirically, assumed volatility is just not constant. And so this is where the opportunity is to apply machine learning. Maybe you can predict what implied volatility will be tomorrow based on what it is today. Or maybe you can use observations of implied volatility to estimate what implied volatility is for assets where you don't have observations. So machine learning really enables a lot of empiricism in finance, in practical day-to-day finance that wasn't possible before. So, the various places that I've worked, even working in research in science or engineering, we want to find good applications for machine learning, and we want to avoid the applications where machine learning is not going to be successful. So identifying an application that's a conversation between the domain experts, so I said business experts here, but the domain experts in general, and the technical experts, meaning the machine learning experts. And in business, I think the biggest opportunities tend to come from making decision-making automatic, where the decision-making now is done by humans. So in finance, this could be bidding in an auction. A lot of assets are sold in auctions that happen very frequently. And there are human traders who decide how much to bid in these auctions. But if we could use algorithms, then we could really scale up. And like the assets that are sold in auctions the most nowadays are advertising slots on the internet. And there's billions of these auctions every day. And so it's totally impossible for humans to participate in these auctions. The humans just write the algorithms that participate in the auctions, and the algorithms use machine learning in order to learn from the outcomes of their bids and then use all available data to come up with what looks like the best possible bid. People talk a lot about data science nowadays, and it's I think one thing that differentiates what I call machine learning from the less useful type of data science, one-off analysis or regular reporting tends to have a lot less business value than actual automation of decision making. So I would really encourage anybody who's working on an application to think how the machine learning can help in a fully automated process. So there you start by identifying the decisions that need to be made. So one important decision for any retailer is issuing purchase orders to the suppliers. And then you work backwards to the predictions that would help make better decisions. And being able to forecast the future demand is going to help you make better decisions about issuing purchase orders. And then once you know what you would like to predict, then you need training data. So you need to work backwards to the historical data that is needed. And often, sadly, you find out that the historical data is just not available. And then if you really want to work on the application, the first thing you have to do is set up all your systems so that they're collecting the historical data. And then when you have enough data, then you can start thinking about building the application. So in general, I'd say machine learning is used to estimate relevant information that is otherwise not available. And one reason it's not available, but not the only reason, is that it's information about the future. It's very important for any application to understand the true business process. So what are the actual decision-making opportunities and what are the actual costs and benefits of those decisions? So something that I've seen on Wall Street, people often talk about probability of default and loss given default. And then they want to use machine learning to estimate these two numbers. But if you look at what actually happens in the life cycle of a loan, many loans are restructured. And so, a good loan is you make the loan and then the borrower pays it back, and then eventually the loan is paid off, and the lender has made some profit from the interest income. And a bad loan, that's a loan where the borrower defaults, and then the lender has a certain recovery, and one minus that recovery is the loss given default. So those are the obvious two types of loan. But if you look in the real world, you see that there are loans that are restructured. And then you may have information about the restructuring, but not about why they were restructured. But if they were restructured, it's quite likely because the borrower was having problems. And if they hadn't been restructured, then they would have become defaults. And the restructuring is a bad outcome for the lender. And so if you make your decision making without taking that into account, you're going to be making too many loans and you're going to lose money on all your loans. And this is just something pretty entertaining. This is from the New York Times from 1990, new terms for Trump from big bank lenders. So this is about Donald Trump restructuring $850 million of debt more than 30 years ago. And the major banks in New York, as far as I know, have refused to do business with Donald Trump for many decades, precisely because they lost a lot of money. Even if they didn't lose money on defaults, they lost money on restructuring. So people often ask me, well, how should you drive a project that uses machine learning? And there's a job category that I'd actually never heard of before I joined Amazon, but I heard about it very quickly. It's very important. And that is what's called a product manager nowadays. And pretty much everything in business is called a product. And the product manager, well, I like to say that, so everything is called a product and everything has users, which are sometimes called customers. And so you want to create a product that is going to satisfy the users. And then there are developers who are creating the product. So the product manager is the interface between the users and the developers. The first question is, is it even worth developing this product? There's going to be a cost to develop the product. So first you quantify the size of the business opportunity. If it's too small, you don't bother. Understand exactly what would be useful for the stakeholders, especially the users and customers. Figure out exactly what metrics you're aiming to improve. Understand which data is useful, find this data, evaluate its quality. design how the new system fits into existing systems. Because if you're doing automated decision making, then almost certainly there are some downstream systems or business processes that are going to consume these decisions. And those systems need to be able to consume whatever the new system produces. And then the data is coming from somewhere. And so the new system needs to be able to consume data from the existing systems. Then if it's a software system, then you need to be quantitative about how fast it needs to operate. That's latency. How much data is going to be involved. That's volume, and many other system needs. There's going to be a user interface. And then very important, there's going to be guardrails and monitoring, because machine learning systems, as I said a little while ago, they lack true intelligence. And so they can go off the rails metaphorically. And so you need guardrails and continuous monitoring to make sure that they're operating in the environment for which they were designed, and they are operating in a sensible way. There's endless ways in which a machine learning application can go wrong, but these are some major ones. Right at the beginning, if there's a lack of consensus on a relevant quantitative objective, very obvious example here in retail, it's very different to try to maximize revenue or maximize profit. Some products some items that you sell are much more profitable than others. So if you were maximizing profit, you would focus on those. But if you were maximizing revenue, you would focus on something different. Another way in which a project can fail right from the beginning is if there are too few decisions and each decision is too important. So at Amazon, several times people ask me, well, can we use machine learning to decide which shows Amazon should produce or which movies Amazon should license for Prime Video? And the answer is basically no. Those decisions are big decisions. They involve many considerations. They involve lots of things that are unknown, for which there really isn't much relevant data. And so an automated machine learning system to make those decisions is just not going to be feasible. Another way in which a system can fail is that, it produces outputs, but they're just not accurate enough. Legal contracts, a company like Goldman Sachs has hundreds of thousands, maybe even millions of legal contracts. And so you want to read those contracts to find out what's in them. And the problem is that natural language understanding is not really precise enough. You'd like to read just imagine a mortgage with a variable rate interest. So you'd like to ask the question, what is the interest rate next quarter? And that involves understanding very precisely the legal language in several different parts of the mortgage. And that's beyond the ability of current natural language methods. Real-time data and or historical data are different and or not available. Sometimes you find that, you have a lot of historical data, but you just don't have the data that you need in real time for making the automated decisions, or the other way around. Then models need to make the stakeholders comfortable. And in finance especially, people really want to feel that they understand what the model is saying and what the model is doing. And so if the model is too complicated, too much of a black box, it may never be authorized for production. And then something very interesting, machine learning methods and really any new technology, they're often held to a higher standard than humans and held to a higher standard than whatever the current business process is. So this picture at the bottom right, this is a drug sniffing dog. And this dog has billions of neurons, and it's really a neural network. And it just barks and wags its tail if it thinks it's found drugs. And but it's completely uninterpretable, unexplainable what it's doing. But law enforcement is willing to trust these drug sniffing dogs, and I guess the courts have not prohibited law enforcement from using them. But I think if you built an electronic machine that had a neural network and said it was doing drug sniffing, I don't think that it would be approved for use. It would be not explainable enough. And actually, this picture is an example also of risk number 4. So this is actually the dog being trained. And you can see that it's being trained on all these cardboard packages, which look almost identical. And so maybe you can train the dog to find drugs in cardboard packages. But then if you use it in an airport to sniff the passenger's luggage, that's the real-time data, which is just very different from the historical data. And so even if it's accurate in training, it may not be accurate in production on the real-time data. When people think about machine learning in finance, I think often people think about predicting future prices and particular predicting future equity prices. And you can be interested in doing that on a time scale of seconds or minutes or days or years. And I can tell you, I don't know how to do that. And I don't know anybody that I am convinced knows how to do it. There are people who think they know how to do it, but they may be just lucky. I don't think that they really have statistically significant evidence that they actually can do it. But so if predicting future prices is too difficult, we can use machine learning creatively to predict all sorts of other useful quantities. The one example, the current value of an asset which is rarely traded. So this is what Zillow does with its estimates. It's not trying to predict what your house is going to be worth next year, although they have started doing that. Mostly what they're doing is just trying to estimate what is your house worth right now based on comps and so on. Very useful also in trading to predict market impact and to predict transaction costs. That can really inform what your trading strategy is. If you're a dealer, then you buy something, you hold it in inventory, and then you hope to resell it. And all the time that whatever you've bought is in your inventory, then it's costing you a carrying cost, and it's risky. It might fall in price while you own it. So expected time in inventory is very useful for dealers to predict. The time course of volume, if you look at, say, shares in IBM, there tends to be a burst in trading earlier in the day, and then maybe rather unpredictable up and down in volume, and then another burst in volume at the end of the day. And the more accurately you can predict when there's going to be volume, the better that you can time your own trading to minimize the negative impact that you have on the market. Then more specific problems in trading, if you want to sell a stock short, you need to borrow it. You may not be able to borrow it, so it's useful to be able to predict what's the possibility of being able to borrow it. And then banks who locate stocks on behalf of their clients, it costs the bank to do a locate, and then maybe the client says, sorry, I changed my mind, I don't want it. And then the bank has done all this work and actually doesn't get paid for all the work. So predicting the probability that your client will actually want to borrow the stock that they ask you to locate is useful. And so this is just 5 examples of things that you can use machine learning for in finance that are not at all trying to predict future prices. And then the less efficient the market is, the more opportunity for profit there is, and the higher the probability that you will be able to predict something about the future. Okay, so people say to me, okay, but I still really, really want to use machine learning to get long-term alpha. And yeah, there's some possibilities here. There's nonlinear extensions of factor models, nonlinear combinations of signals from financial statements. There's a whole industry nowadays of applying natural language to 10K statements and other statements, forward-looking, risk section, CEO descriptions of business. Something which turns out to be quite useful also is choosing comps objectively for assets. So, let's say you you are buying a house and you need to estimate, how much is this house worth? So your agent may say, well, look at these 3 other houses and they're worth this much. And so the one you're looking at is worth this much. But the agent may have chosen 3 comps which are overpriced, or they may have chosen 3 comps which are low priced. And so they're choosing the comps subjectively to drive the answer that they want. Well, a machine learning method can choose comps in an objective way that is not biased towards any desired outcome. So I mentioned natural language processing on financial statements. So the state of the art doesn't really let you answer very precise questions like what is the interest rate next quarter, but you certainly can measure qualitative characteristics like sentiment and obfuscation, like, is this CEO being plain and simple in describing the business, or is this CEO trying not to reveal a lot? And then I think there's an opportunity in forecasting financial results. If you think about it, when a company announces its quarterly results, what it's announcing is something that was actually true at the end of the quarter. And it took the company several weeks or even months to just assemble the data to do the calculation of what the quarterly result was. So if you can use data to predict what the quarterly results are faster than the company can actually calculate the results, then that's a significant opportunity. This is an article from Bloomberg a few years ago. Hedge fund founder and Amazon researcher built a better AI stock picker. The headline is exaggerated, but what this is actually about is forecasting quarterly financial results. And I chose this because the second author, Zach Lipton, he was my PhD student at UCSD. He's currently faculty member in machine learning at Carnegie Mellon. So maybe that's also indirect evidence that it is too difficult to use machine learning to predict future prices, because if Zach was really successful, then probably he would be a trader and not a machine learning professor. And if I was really successful, I'd probably be a trader rather than working for Saks Fifth Avenue part-time. All right, I think I've probably gone on too long, so I'll stop here. Questions, very welcome.
One of the first ones that came in was, what did you see was the biggest difference in the life of a machine learning researcher at Amazon versus Goldman Sachs? How did they look at machine learning differently?
Well, yeah, 2 big differences. One is that when you're in retail, there's much more signal in the noise. So finance is much more competitive, and so there's much less signal in the noise. And whereas if you're trying to predict something about the behavior of consumers, that doesn't really change over time. If somebody watches the first Harry Potter movie, then it's pretty likely that they're going to be interested in buying Harry Potter merchandise. And the other difference is that, probably connected, a company like Amazon and generally the tech companies, they can think longer term than Wall Street companies. Wall Street companies, they really are thinking about today's trading or today's deal, and everything has a lot of time decay, and data from far in the past is just not useful. There's endless numbers of papers published in the finance literature where people find predictive patterns in historical data. And but that is really of little interest on Wall Street, where the question is, what is predictive about today's data?
Right, interesting. So there's a number of questions around kind of AI and where is it now, where is it going? And a lot of them are also related to this issue of what will be the impact of machine learning and AI on workers. So do you think it will be more about augmenting the skill and kind of boosting productivity, or will there be lots of displacements? How do you see that? And then related to that, as it evolves, what's kind of the longer term view that you think it will be able to achieve?
Well, I mean, we always want to talk about augmenting and not replacing. We always want to talk about letting people do the parts of their job that are more interesting and automating the parts that are less interesting. But the reality is that as you augment, if there's a finite amount of work to do, then there are going to be fewer people doing that. So if we can reduce the average time for a primary care visit from 25 minutes to 9 minutes, when you decrease the cost of something, then just where the supply equals demand at a higher volume. So the volume of primary care visits is going to go up, but it's probably not going to go up threefold. And so probably we're not going to need as many primary care providers as we have nowadays. But any social evolution like that is very slow, very long-term, multiple decades. And it can be very hard to measure because it's superimposed on all sorts of other phenomena like recessions and other shifts in the industry, like maybe nurse practitioners taking over from physicians or something else. But Jeff Bezos has a great answer when you ask him about the impact of automation on employment, and which is that there are obvious areas in society where we just wish we had way more people working in those areas. Imagine if every classroom had 2 teachers. Imagine if every child in school could have individual tutors in every subject in which that child was having difficulty. There's huge need for labor in large areas of society.
I think that's a great answer. So let me jump into a couple of these other ones. Is the deep learning limitation due to lack of good algorithm, good data, or computational limits?
I think it's due to lack of good algorithms, but it's not that we're going to have a good algorithm tomorrow by tweaking the current ones. There's still some fundamental insights into intelligence that we just don't have scientifically. I think there's a good analogy with intelligent life on other planets. There's no reason to think that it's impossible, but we don't have any evidence for it either. And I think that's the situation with true artificial intelligence. There's absolutely no reason to think that it's impossible, but we definitely don't have the basic scientific concepts yet that would produce it.
Right. There's not a clear path to getting it, and if there was, we would be there.
Yeah, there is no clear path to getting it.
Okay, that makes sense. Do you see screening and due diligence in VC investing as a good use case for ML?
Well, no. I think it's similar to, and maybe even more difficult than green lighting a movie. Just because, here's a good example. So the Lord of the Rings movies were very successful. And so Amazon, for what I read in the media, Amazon spent $450 million, more than any TV show ever before, on making the first season of Lord of the Rings TV. And they're canceling it after the first season. And I think they're canceling it even before they've shown it to viewers. So I don't see how you can use machine learning to make $450 million decisions.
Okay, that makes sense. So let me add one that I had as well, which was related to things like AutoML. So when I tell my students about the advances there, and that in some sense, cross-validation and hyperparameter tuning is kind of boring, like, oh, wait, if AutoML can replace that, what are we going to be left with? So how do you see the role of data scientists developing as we get more tools like AutoML to be able to generate good predictions for us?
Well, I'm somewhat skeptical about AutoML. It's a huge opportunity for overfitting.
Right.
And most of the work is not in finding the optimal hyperparameters for the things that AutoML can do. The most of the work is in obtaining the data and then understanding the business domain. For example, so let's say you're trying to predict real estate prices, you're trying to build Zillow's estimate, and you have a bunch of comps, and those comps were a certain length of time in the past. Well, like intuitively, how much worse is 3 months old compared to 2 months old, and how should you code that as input to your model? Human understanding of the domain is going to be valuable.
Right. Let's see. Where do you feel that AI can replace financial analysts, and where do you think they cannot?
Mm-hmm. I think, on the one hand, I think a lot of the work that many financial analysts do, and no offense to anyone, I think a lot of it is just not useful, because essentially they're trying to predict future stock prices, and I think not many of them have a very good track record. And then on the other hand, they're doing so many different things. They're talking to management. They're trying to read between the lines of statements. They're going out and talking to customers. And so most of that work, can't be automated. And then the good ones are putting, judgment on top of all the information that they're collecting, and that judgment is probably not much easier to explain than what the dog is doing when it's sniffing luggage for drugs.
I thought that was a really interesting analogy about the dog. You're right. So maybe we have just 1 or 2 minutes left. Would you be willing to tell us a little bit about your startup and what you're trying to accomplish?
Yeah, so we're building really technology for automated bids and automated offers in fixed income. So there's there's thousands of publicly traded stocks, but there's actually millions of traded bonds, and many of them are very illiquid. And so you need to take into account a lot of factors in deciding how much you're willing to pay or how much you're willing to accept if you own it already, including the correlations. Dealers are very concerned about reducing their risk. If they already own something, they want to buy something which is anti-correlated, and they don't want to buy something which is positively correlated.
Right.
And so there's so many considerations that go into trading. Many dealers just don't have the bandwidth to participate in essentially all the auctions that they could participate in. Right.
Okay.
Then it's not it's not just the dealers. The whole ecosystem, like underwriters don't know whether they're getting a good deal. So issuers don't know whether they're getting a good deal from their underwriters, and so on.
Got it. So I believe we are going to 6 p.m. So I want to really thank you for your time, Charles. It's been fantastic to have you come out. We will definitely keep you on radar to see how things are going with your new startup. And I hope we can get you back at some point in the future to talk more about what you're up to.
Yes. Well, thank you, Vincent. I hope the next time we'll be live.
I hope so too. Thank you so much. And thank you everybody for attending this evening.